This presentation is by Cigre Kuwahata from Ampasimon on the topic of application examples of dynamic line rating for connect and manage in Belgium, Netherlands, France, and Germany. I'm Cigre Kuwahata, heading business development at Ampasimon. My experience centers on renewables grid integration and power system flexibility. I started my career in Australia, where I carried out connection compliance studies for new generation like gas and wind power while I worked at AEMO. Since 2010, I've been in Europe, where I've contributed to the energy transformation discussion with grid modeling and power flow studies with high penetration of renewables and testing the effectiveness of various flexibility options. Before I launch into the presentation, I want to let you know that there's a Japanese version of this presentation on YouTube. For the Japanese version, please follow the link. Distributed energy resources, or DER, like renewables, electric vehicles, and active prosumers are growing at a rapid pace. This is actually not unique to Europe, it's a global trend. To distribute the benefit of cheaper energy across wider geographic scope, various aspects of power supply is transitioning to market-based procurements. We're seeing this in the form of transitioning to wholesale dispatch markets, capacity markets, balancing reserve markets, and some ancillary service markets. Market rules are changing, but the market efficiency goals can only be achieved if the grid enables the transaction of flows. The problem is that grid reinforcement has much longer lead times than DER, and project realization is delayed by public opposition. To catch up with the new grid paradigm and to release the benefits from market efficiency, there's pressure to reform operational solutions to problems traditionally solved by reinforcement. This is where dynamic line rating can be used. Today, I'll introduce some applications of dynamic line rating in Europe that are helping to manage the power flows from renewables after they've been connected. In Europe, most countries have tested some kind of dynamic line rating system in the past decade. The countries marked in green and purple on this map have conducted pilots in the past. Of these, I'll introduce applications in Germany, Netherlands, Belgium, and France, as each of them have strong impacts from power flows caused by renewables and use dynamic line rating to help them manage these impacts. These countries are interconnected neighbors and are subject to some common European rules about how to use transmission capacity. However, the way they use dynamic line rating differs because the main driving business case is different due to local specifics. Different types of dynamic line rating is used in each of the 4 countries. In Belgium and France, line-mounted sensor-based dynamic line rating is used. In the Netherlands, they use the same line-mounted sensor, but the measurements are used to validate a computer weather modeling-based dynamic line rating. In Germany, they prefer to use dynamic line rating systems based on computer modeling of weather only. With this method, the dynamic line rating accuracy is low, and this is why they install weather stations to improve the data quality, like those shown in the picture on the right. There can be several drivers for applications of dynamic line rating, but the biggest one by far is the rapid development of renewables. In the focus area, we see that there's been strong growth of renewables like wind power in the north of Germany and north of France, offshore wind in North Sea area, and also there's been strong growth of PV plants in the south of Germany and France. However, the demand centers, marked here as the capital cities like Paris in France and industrial centers like Stuttgart in Germany, these are not co-located with the generation. This means it causes large amounts of power to flow from north to south through all available transmission lines. For example, in Germany, the high loading is cause for concern of overloading. The German TSOs call the thermal power plants to change their production schedule and compensate them for the redispatch service, while on the other hand, they curtail in-feed from wind power plants and also pay a compensation. This congestion management cost is reaching €1 billion each year. Because power flows on the transmission grid is getting higher, new reinforcements are being planned. However, there are restrictions on the development because of public opposition to new overhead power lines. The projects are being delayed in Germany. In the Netherlands and Belgium, the regulator has limited the amount of overhead line projects that can go ahead. It requires that new capacities should be undergrounded, significantly increasing the reinforcement costs. In addition to this, in Belgium, the national power supply and grid infrastructure is reaching the end of its lifetime. The aging grids needs replacement and upgrades, which means they are constantly dealing with major maintenance outages. In France, until recently, there were no requirements to prioritize connection of wind farms or compensate them for curtailment. However, the government has decided to accelerate wind power development and change the rules on curtailment. This means the French TSO has to be more aggressive on how they define hosting capacity and consider how to manage the high power flows. The top concern brought about by the energy transition in Europe differs slightly from country to country. Now we get into the part, how is dynamic line rating used to solve these challenges? First of all, you have to understand that each TSO monitors and controls its transmission grids 24/7 from a control center. Here, power flows, voltages and frequency are monitored not so much in real time, but in an operating planning time frame. This allows the operators to take preventive action in case they see a risk of overload or imbalance that can cause the system to collapse. So-called intraday operational decisions are largely made on the expected power flows resulting from forecast demand and forecast generation, including renewables. Some hours ahead of real time, power flow simulations are made based on these forecast information, including forecast dynamic line rating, and the operation of grid equipment like substation switching, transformer tapping, and HVDC terminal control are planned. For example, the Belgium TSO ELIA uses the 1-hour forecast dynamic line rating directly in the SCADA and EMS for intraday operation. You can see from this screenshot that the names of the lines are listed, the power flows in MVA, the conventional static line rating, as well as the 1-hour forecast dynamic line rating values. This is one of the screens that the operators use to make operational decisions. There's also a web-accessible display of information where conductor temperature and sag can be monitored in real time. I explained that forecast information is the most important for grid operation. So then what is real-time data used for? Besides monitoring the sag and conductor temperature to ensure asset safety, the real-time measurements are used also for validating forecast data. Forecast dynamic line rating relies on weather forecast information. The difficulty of predicting weather, especially low wind speeds close to the ground and in complex terrain, is well known to weather modeling experts. By having continual real-time measurements, the forecast dynamic line rating derived from weather forecast can be checked and improved with a learning algorithm. This means the longer you have the system installed, the more accurate the forecast dynamic line rating becomes. To demonstrate this point, here is a graph comparing the wind speed values. The red curve is the forecast wind speed from a weather forecast provider, like the Bureau of Meteorology. The green curve is the actual real-time measurement. The blue curve is the forecast wind speed, which is generated by applying the machine learning algorithm, which constantly compares the red forecast with real-time measurements. The vertical axis shows the wind speed in meters per second and the horizontal axis the time of the day. You can see in the middle that the wind suddenly drops from around 3.5 meters per second to 0.75 meters per second. The impact of such a drop of wind on the dynamic line rating is significant, causing a reduction in capacity from 50% extra to almost nothing in about an hour. If the line is highly loaded, you would like to know the reduction in the capacity with anticipation, so that you don't inadvertently overload the line. However, if you use the red forecast wind speed for calculating dynamic line rating, you would end up with a significant overestimation of the capacity. This is why forecast wind information must be corrected or downgraded to reduce the risk. With an intelligent learning algorithm which continually compares the forecast against real time, it can learn from the traits of the wind in that location and the type of forecast data. The blue curve can be controlled with a confidence interval. For example, it could be set to release extra capacity from wind cooling effect with a statistical confidence of 98%. This means that the blue curve would be below the actual real-time wind speed 98% of the time. The accumulation of real-time data, so historical data, can also be used in statistics-based decision-making. For example, in Germany and France, the benefit of increased capacity by dynamic line rating is used for long-term grid investment planning. We've been doing this for over 10 years now, and we know that generally, this monitoring technique gives you more than 10 to 20% extra capacity most of the time. This graph shows the duration curve of the real-time dynamic rating in green compared to the conventional static limit in red. The static limit is always, so 100% of the time, as indicated on the horizontal axis, at the same value. This is why it's a fixed straight line. While the dynamic rating is sometimes twice the capacity of the static rating, sometimes 30% extra, sometimes 5% extra. depending on the weather. So from this graph, you can see that 90% of the time, the green line is at least 20% higher than static limit. How can we quantify the benefit of dynamic line rating specifically for wind integration? To help visualize this, here's an illustrative example. For our 150 kV double circuit line, the N-1 limit based on static line rating is shown as the horizontal red line at 170 megawatts. Normally, wind connection would be limited to this hosting capacity. So for example, a 150 megawatt wind farm can connect right away, but if you want to increase the size to 240 megawatts, you will have to wait a few years until the grid is reinforced. The infeed from a 150 megawatt wind farm is shown as the blue dotted line. You see that it never exceeds the static rating, which is the red line. This means all of the production can be accepted by the grid and no curtailment results. However, if the grid operator is able to manage potential overloads with various congestion management options, maybe he will accept the connection of a 240 megawatt wind farm without waiting for the grid reinforcement. The infeed from a 240 megawatt wind farm is shown as the solid blue line. You see that this sometimes exceeds the static rating, which means the energy may be curtailed. However, if the grid operator uses dynamic rating instead of static rating to determine the N-1 limit, the red line shifts to the green line. Then, any infeed exceeding this must be curtailed, but anything below it can be safely accepted by the grid without causing any overloads. So you can see that it's suitable for managing high load situations. This extra capacity for renewables integration can be visualized like this. By traditional approach, you would only allow maximum connection capacity based on a static line rating. So in this example, around 150 megawatts maximum could be connected to a 150 kV line. However, if you use dynamic line rating, you know that the real limit looks like the green line. This means you can accept a higher connection capacity and accept a higher amount of wind power into the grid without violating the limits. It's been found that the hosting capacity can be increased by up to 50% without the need for reinforcement if the dynamic line rating is used together with curtailment compared to the traditional approach. We're coming towards the end of the presentation. I'll now summarize with some conclusions. Dynamic line rating gives capacity benefits. This was proven by applications in Europe. The most prominent of which is that it can increase hosting capacity by up to 50% if used in combination with curtailment, and that it's very effective in relieving congestions. Where there is a penalty cost for congestion management, like redispatch and curtailment, it can create savings in the order of €500,000 in a day. Relieving the bottleneck to increase the market access of low-cost energy can also create enormous benefit. Reported from Belgium was €250,000 in 4 hours. In Europe, these strong business cases drive the adoption of dynamic line rating on a larger scale. Dynamic line rating is considered in national development plans of Germany and France. The effect of dynamic line rating in relieving congestions for renewables and market integration is recognized by the European Commission, so that they were able to set the requirement to TSOs to release 70% of cross-border transmission capacity for power trade. Finally, dynamic line rating is expected to continue contributing to the energy transition by delivering concrete results in accelerating renewables connection, reducing curtailment costs, and creating quantifiable social benefits. This is how dynamic line rating should be used to connect and manage renewables.